Welcome to Chemical Reactions and Equations. So, a chemical reaction is a process which brings about a chemical change in one or more substances. So, this is a chemical change as opposed to a physical change. For example, we perform a chemical reaction when we burn hydrogen gas, this is H2, to produce water vapor, H2O, and we have this little subscript G in parentheses to indicate that this is a gas phase water, so it's not liquid water that we're producing here. And so note here that when we say we burn something, that means that we are going to react it with oxygen gas, so O2. So in chemistry, we want a way of succinctly stating the substances that we start with and the substances that we end with in a chemical reaction. Now, writing these in words is fairly lengthy, and we want a shorthand way of writing these down. So instead, we use what's called a chemical equation, in which we use the chemical formulas to display what the reaction is. For example, for our burning of hydrogen gas to produce water vapor, we can write the chemical equation like this. So we have 2H2 gas plus O2 gas yields 2H2O gas. And there are two ways of reading this equation out loud. We can say 2H2 plus 1O2 reacts to form 2H2O or yield 2H2O. Or we could say 2 molecules of hydrogen plus 1 molecule of oxygen reacts to form 2 molecules of water. So remember that if we don't have any coefficient written here, then that means that we really have a 1. So we have 2 molecules of hydrogen gas reacting with 1 molecule of oxygen gas to yield 2 water molecules. So the substances that are on the left side of our arrow are called the reactants. These are the things that are reacting together. The reactants are used up during our chemical reaction. In other words, they're the things that react together to make something new. And the substances on the right side of our arrow are called the products. So in this case, the water is our product. The products are formed or produced during the reaction. So these are the things that are new that we didn't have around before. So before the reaction, we have hydrogen gas and oxygen gas. After the reaction, we have water. And we've used up some or all of our hydrogen and oxygen. We've produced water that wasn't there before. So we can provide even more information if we use the structural formulas of the substances involved instead of the chemical formulas. For example, for the reaction between hydrogen and oxygen, we can have something like this. So we've got 2 molecules of H2, and now you see that we've separated H2 into 2 hydrogen atoms. We're showing that they're bound together because those atoms are touching. And similarly for the oxygen, we've got the 2 oxygen atoms. In this case, you can actually see that we've shown the oxygen atoms as being physically larger in size than the hydrogen atoms are. And so we've got 2 molecules of H2 that are reacting with 1 molecule of O2 to form 2 water molecules, 2 H2O. And so in these molecules now we have an oxygen-hydrogen bond here, we have an oxygen-hydrogen bond there, and we've got 2 groupings of that. Those 2 groupings are separate, so we've got 2 separated molecules. So we're going from 3 molecules down to 2 molecules. So by writing our structural formula, we can more easily see that not a whole lot has changed. We started with 4 hydrogen atoms, 1, 2, 3, 4. We started with 2 oxygen atoms, 1, 2. We end with 4 hydrogen atoms, 1, 2, 3, 4, and 2 oxygen atoms. So all that we've done is change how those atoms are bonded together. Beforehand, the hydrogen atoms were bonded to each other and the oxygen atoms were bonded to each other. And after, we've broken those hydrogen-hydrogen bonds and the oxygen-oxygen bond, and we formed oxygen-hydrogen bonds instead. So this brings us to one of the fundamental laws of chemistry. In a chemical reaction, bonds break and bonds form, but the number and kinds of atoms never change. And this law is sometimes called the law of conservation of atoms or the law of conservation of matter. So before, during, and after a chemical reaction, there is also a conservation of mass. That is, the total mass of the reactants must equal the total mass of the products. And this makes sense since we're not changing the number of atoms or their identities. That is, the masses of the atoms must remain the same, and if the mass of each atom remains constant and the number of each atom remains constant, then the total mass must be constant. So all we're doing here is rearranging where the atoms are, where the atoms have their bonds. But we're not changing the masses of the atoms, we're not changing the identities of the atoms, so the total mass that we had before has to be the same as the total mass after. So if the number of atoms, the identity of those atoms, and the total mass aren't changing, then what does change in our chemical reaction? Well, the way the atoms are arranged will change. We may form or destroy compounds, but not the atoms that compose those compounds. And if the compounds are being formed or destroyed, then the chemical properties of the substances involved are changing. We also change the energy that's contained in the substances involved in a reaction. That is, the chemical reactions can cause energy to be absorbed or released during the reaction. And energy can be absorbed or released either as heat or as light or as work. In fact, we can actually include energy as either a reactant or a product to explicitly show whether the reaction is absorbing or releasing energy. For example, the reaction between hydrogen and oxygen releases energy because we're burning the hydrogen, so we have 2H2 plus O2 yields 2H2O plus energy. So we're getting energy out, and this is why the combustion of hydrogen can provide energy for things like running hydrogen-powered cars and things like that. Now, unless we're focusing on the energy involved, we generally will omit the energy from the chemical reaction. Now let's look at another chemical equation. In this case, the combustion of octane, which is the primary component in gasoline that we use in automobiles. So here we have octane is C8H18, and we have 2 molecules of octane plus 25 molecules of oxygen, yielding 18 molecules of water and 16 molecules of carbon dioxide. So in that octane formula, C8H18, that 8 is a subscript. The 18 is also a subscript. Now, a subscript tells us how many atoms of the element immediately to the left are present in each molecule or formula unit. So in this case, we've got 8 carbon atoms and 18 hydrogen atoms. Now, if we don't have a subscript written, such as after the O in H2O here, then the subscript is assumed to be a 1. So we have 1 oxygen and 2 hydrogen atoms in every water molecule. Now, in this first term over here, that 2 is what's called a coefficient. Now, the coefficient tells us how many particles, so this is either atoms or molecules or formula units, of the species, the element, ion, or compound, to the right that are involved in the reaction. So in this case, our 2 here tells us how many octane molecules are involved. The 25 coefficient there tells us how many oxygen molecules are involved. That's not oxygen atoms, because we have twice as many, so we have 50 oxygen atoms involved, but we're not reacting the octane with oxygen atoms, we're reacting the octane with oxygen molecules. So, if the number and kind of atoms on each side of the arrow is the same, then we say that the equation is balanced. So here I have a balanced equation. The coefficients of a balanced equation show us the exact ratios in which the particles react and form. So, we have 2 molecules of octane reacting with 25 molecules of oxygen. So, the octane to oxygen ratio for molecules is 2 to 25. We then produce 18 water molecules and 16 carbon dioxide molecules. So if we burn 2 octane molecules, we get 18 water molecules. And if we burn 2 octane molecules, we get 16 carbon dioxide molecules. So in order to count the total number of atoms of an element present, we multiply the coefficient by the subscript for that element. For example, we've got our equation here. If we're looking at carbon on the left side of the arrow, we have no carbon involved here in this formula, so we're going to ignore that one, and we only need to look over here. So we have our coefficient 2 times the subscript 8, that gives us 16. Now that's occurring because we have 2 molecules of octane. In each octane molecule we have 8 carbon atoms. So in each molecule we have 8 carbon atoms, we have 2 molecules, so 2 times 8 gives us 16 carbon atoms. With the hydrogen, we've got 18 hydrogen atoms in each octane molecule. We have 2 octane molecules, so 2 times 18 gives us 36 hydrogen atoms. And we can do the similar sort of thing on the right side. So over here, for carbon, we have 1 carbon atom in each carbon dioxide molecule. We have 16 carbon dioxide molecules, so 16 times 1 gives us 16. And you note that this number here, 16 carbon atoms on the right side, is the same as the 16 carbon atoms on the left side. That means that the equation is balanced for carbon. Now let's look at hydrogen. In water, we've got 2 hydrogen atoms in each water molecule, and we have 18 water molecules, so 18 times 2 gives us 36. So we had 36 hydrogen atoms on the left side, we have 36 hydrogen atoms on the right side, so the equation is balanced for hydrogen. And now we need to look at oxygen. So if an atom is contained in more than one species on one side of the equation, or on both sides, then we multiply the coefficient by the subscript separately for each species, and then we add the results together. So on the left side, oxygen is only in the oxygen molecule. We have 2 oxygen atoms, 25 molecules of oxygen, so 25 times 2 gives us 50 oxygen atoms total. But on the right side, we now have oxygen here in our water, but we also have some oxygen over here in our carbon dioxide. And this means that now we're going to do the same thing that we did before, 18 times 1, plus now the oxygen that we have over here, 16 times 2. So that gives us 18 plus 32, which is 50. And now you can see that we have 50 oxygen atoms on the left, 50 oxygen atoms on the right, so we're balanced for oxygen. There are no other atoms involved, and so the chemical reaction is balanced. And that was chemical reactions and equations.